we are back with Chapter 3, Probability. This is our second week in this setup of me talking to you through the computer. So, probability is a nice little chapter. Looks relatively small. The problems for this chapter can get pretty big, but the concepts behind them are pretty small. So, these are the four things we're going to be looking at. So, what is probability in 3.1? What's a sample space, and what's an event in 3.2, and then some elementary rules in 3.3, and then we're going to be looking at conditional probability and independence, and that's kind of a tricky concept. This section here, 3.4, that's tricky. So, moving along. What is probability? So, we're going to be using this word experiment quite a bit. So an experiment is any process of observation with an uncertain outcome. So, I mean, what's the trope? Like flipping a coin, right? So I flip a coin one time and that's an experiment, right? We don't know if it's going to be heads or tails. The possible outcomes of an experiment are called the experimental outcomes. Okay, so in our example before with heads or tails, I flip a coin and the experimental outcomes are either going to be heads or tails. Now, probability is a measure of the chance that an experimental outcome will occur when an experiment's carried out. So, just imagine I flip my coin and I either get heads or tails. And what would be the outcomes? Well, there's a 1/2 chance that it's heads and a 1/2 chance that it's tails. Why? Because there's only one way that it can be heads out of the two possibilities, heads or tails. Yeah, there you have it. If only we could stop there. All right, so we're just going to get used to some letters and other things here. So if E is an experimental outcome, then P of E, notice how I say this. I say this P of E. P of E, that's just some math lingo. P stands for probability and E stands for experiment. So we might also say, probability of E. Probability of E. And I did finally get a stylus. Do you like it? So, the probability of E denotes the probability that E will occur, and a couple conditions here for any experiment. The probability of E occurring always needs to be between 0 and 1. So what this is saying, what this says in math, is that it needs to be between 0 and 1. So we can write that. So, probability of E occurring is between 0 and 1, such that a 0% chance of something occurring would be written as follows. So you'd write probability of E in brackets equals 0. So that's how you would write that there's a 0% chance of this occurring. And a 100% chance of something occurring would be written as probability of E equals 1. So you'll notice that we write percentages as whole numbers, right? 100% is 1. When you have a percentage, you divide by 100 to figure it out as it is, as a decimal, right? So if it was 81% as a decimal, I would just divide it by 100, and as a decimal, 81% would be 0.81. So that's just a little thing to remember from, I guess, previous math that you may have done in high school and earlier. The probabilities of all the experimental outcomes must add to 1, or 100%. So when you have an experiment, so take our heads and tails experiment from before. When you add up all the different experimental outcomes, so in our example, there's heads, which has a 50% chance, and tails, also a 50% chance. When we add up all the different outcomes, so add up heads or tails, you need to get 100. That is a fundamental rule of probability, that all the outcomes added up must be 100% or 1. And we use that fact to solve some problems eventually. So, the classical method, yes. Let's talk about that fair coin, that head toss, that coin toss. So, when all the experimental outcomes are equally likely to occur, example, tossing a fair coin, Your textbook will make mention a lot to fair coins and fair dice. I don't know why, but I guess that's something people argue about. But the two outcomes here are heads or tails. If the coin is fair, then heads and tails are equally likely to occur anytime the coin is tossed. So the probability of heads is a couple ways that we can write it. We can write it as 0.5, like this. Probability of tails is also 0.5. You might also write it as a half and a half. Okay, either one's fine. Check and make sure the probabilities add up to 1. Well, probability of heads plus probability of tails must equal 1. Notice how I wrote this. Okay, so you'll get used to writing probabilities like this. So probability of heads is 0.5 plus the probability of tails is 0.5, and oh boy, does that equal 1? Yes, 1 equals 1. Hooray! So I might bore you with kind of this really straightforward example, but my purpose here is to get you to notice the notation. Okay, so it's very important that you're familiar with the notation. We usually write P for probability, and then in brackets, we'll write what the probability is for, or the letter, like H for heads. Just notice the notation. It'll be very important as we move forward. So, what is the relative frequency method? Well, let E be the outcome of an experiment, and if the experiment is performed many times, the probability of E is the relative frequency of E. Remember that this word relative frequency is just a fancy way of saying a fraction, right? So usually relative frequency type problems, we either use a sampled or historical data to calculate probabilities. So for example, here's a sampled data question. 1,000 randomly selected consumers were surveyed, and 140 preferred Coca-Cola. What is the relative frequency of consumers preferring Coca-Cola? So we might write something like this. Well, the probability of Coca-Cola, so C for Coca-Cola, is equal to, well, what's the relative frequency? 140 people surveyed out of 1,000. Okay, now you can leave your answer like this. You don't need to necessarily reduce it down. Like I could easily divide the top and the bottom by 10 and get 14 out of 100, or 0.14. All of these answers would be fine. Okay, you just got to write one of them. You could also say 14%, right? So if you have a decimal, you multiply by 100 to figure out the percentage. Likewise, if you have the percentage, divide by 100 to get the decimal. Unless I'm asking for the answer to be in a particular format, any of these answers here would have been fine. Wonderbar! Let's talk about something called a sample space. So the sample space of an experiment is the set of all possible experimental outcomes. Basically, we diagram it out. Okay, so the sample space is sort of a visual representation of all the possible outcomes of an experiment. Here's an example predicting the gender of a child. So a newly married couple plans to have 2 children. Calculate the probability of all the possible outcomes for this scenario. Show the sample space as well. Perfect. Now, let B denote that a child is a boy, and G denote that a child is a girl. This is a nice step. Okay, it's good to sort of tell the reader what your letters mean, so that B is boy and G is girl. You don't always have to do that. Like, it can be pretty obvious in this question, but it also might not be obvious. You don't necessarily have to do it on a test. Usually I will present things to you with the letters already like this, okay? So just a small aside before we begin. All right, so what is the sample space? Well, check out this neat little diagram I have over here. So you kind of start here, and this is your first child. And you branch out because there's 2 possibilities. It could be a boy or a girl. Okay, now you have your second child. So say you have a boy, so if you follow this branch, well, you have another kid, and it could either be a boy or a girl. So this stream leads us to figure out, well, we could have a boy-boy, or we could have a boy-girl. Okay, what if we had a girl the first time? Well, if we had a girl the first time, the second time we could have a boy or a girl. So you got girl-boy and girl-girl. And what we have here, these 4 things, this is the sample space outcome. So here it is diagrammed, and sometimes I'll just say, well, can you list the sample space? And the answer is yes. I will use these weird curly brackets that nobody can draw, or at least I can't. And we could have boy-boy, boy girl, girl boy, or girl girl. And then close your curly bracket. So this is the sample space. This represents every single possibility of this, this experiment, okay? So once you know the sample space, what's the probability of having a boy? Well, has it changed from half, right? Like, look, probability of having a boy is still 0.5. Probability of having a girl is still 0.5, right? Every time you do the experiment, it's half a chance for a boy, half a chance for a girl, right? Now, what's the probability of having a boy-boy? Well, look, there are a total 4 outcomes. So n is 4 in this experiment. So when you have 2 kids, there's 4 outcomes. So the probability of having boy-boy, look at your sample space. It's 1. There's only one way for that to happen. So it's a quarter. Or you might write 0.25. You can type it in on your calculator or whatever. What's the probability of having a boy-girl? Well, again, if you look at the sample space, there's only 1 out of 4 possible ways that can happen. Okay, what about girl-boy? Same thing. If you look at the sample space, it's a quarter. What about girl-girl? Again, it's a quarter. Perfect. Let's continue along on this little journey of an example. So, the probability that the couple will have 2 boys, well, we already said that that's a quarter. Right now, what if you were going to do this without the sample space? Okay, so we know we did the sample space, we know the answer's a quarter. So what if without the sample space, I just said, well, what's the probability of having boy, boy? Well, here's how you would do it. You'd say, well, the probability of having the first boy is a half. And then you would multiply by what's the probability of having the next boy? Also a half. 1 times 1 is 1. 2 times 2 is 4. So you get 1/4. Okay, so that's how you would do the problem if you were not going to draw up the sample space and figure it out. Sample spaces are nice, but for more complicated questions where you have, say, hundreds of outcomes, it gets very hard to map out the sample space. Okay, so eventually we'll be gravitating towards doing questions this way, but it is important to know the whole sample space concept. Probability that the couple will have one boy, will have a boy and a girl. Well, we'll have one boy and a girl. Notice how it's not stipulating that it happens in a certain order, right? Just have one boy and one girl. Well, there's 2 ways this can happen. Right? You could have a girl and then a boy, or you could have a boy and then a girl. That would satisfy what the question's asking for. So how many ways are there to have a girl and then a boy? Well, we know from the sample space that it's a quarter. How many ways are there of having a boy and then a girl? Well, we know that there's 1/4 ways of doing that. The word or in probability generally means addition. So probability of one, oops, I meant to write one boy and one girl is equal to a quarter plus a quarter, which is equal to a half. All right, or 50%, right? You can write your answer as a percentage or as a decimal. For now, I'm sort of writing out all the possible ways you can write out the answer, but I'm not going to be doing that all the time. I tend to leave it as a fraction. All right. Probability that the couple will have 2 girls. Well, there's only one way to have 2 girls, right? You have a girl and then you have a girl, right? So without looking at the sample space, that's 1/2 chance of the first girl times 1/2 chance of the second girl. So by the way, it is multiplication when you write brackets together like this. I'm assuming that you know that. And if you don't, now I've reminded you. There you go. So 1/2 times a half is a quarter. Now again, this one here is the probability the couple will have at least one girl. Well, at least one girl would mean what? Well, I could have a boy and then a girl, or I could have a girl and then a boy, right? That's at least one girl, or at least one girl could be girl, girl. So there's a 1/4 chance of this happening, or means addition. There's a 1/4 chance of that happening from our sample space. Or girl, 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 girl is also a 1/4 chance. So probability of at least one girl equals, and yes, you can write a little phrase in here if you want. So probability of at least one girl is a quarter plus a quarter plus a quarter, which is 3/4 or 0.75 or 75%. Wonderful. I'm glad. I really like this question. It's about as simple as a more complicated question can get. It shows you what a sample space is, a little brief introduction on how you can multiply probabilities together when you add them. So when the word is or, right, then you add probabilities. Otherwise, you're generally multiplying them. It kind of wraps up everything that we're going to get to in a lot more depth by the end of this little presentation. So let's talk about this. Probabilities, equally likely outcomes. So if the sample space outcomes or experimental outcomes are all equally likely, then the probability that an event will occur is equal to the ratio of, this is what I was just doing on the last one. So the number of sample space outcomes that corresponded to the event divided by the total number of sample space outcomes. So in our question before, we had 4 outcomes. And then, what the event was depended on what we were looking for, right? So if we were looking for, probability of boy, well, then there was only one way that could happen. So we did 1 divided by 4 to figure out that outcome. This is a very basic sort of concept to probability, but in general, this is always the case. The number of possible outcomes that correspond to the event you're looking for divided by the total number of outcomes. That will find you the probability of most things. So let's talk about these elementary probability rules. And maybe now is a good time, before I show you this, to show you that this is the formula sheet that we have so far, and it'll be posted to Moodle. So basically what I do in this course is, instead of just giving you the final formula sheet and scaring you with its 4 pages of huge formulas, I just build it up week by week. Okay, so from last week, these are the formulas that we basically covered. So in ungrouped data, this is how I organize my formula sheet, reminding you of the sample letters that we use for mean, standard deviation, variance, and proportion, and then the population letters. Okay, so that reminds you of that up there. And then we did the mean, so it's the sum of every xi over n. We did standard deviation, okay, this formula. If it's the population version, the difference, remember, n minus 1 for sample and n for population. Okay, and then it's got the variance formula as well, reminding you the median is the middle reading, that range is highest minus lowest, and that interquartile range is Q3 minus Q1. And I also threw in the correlation coefficient of standard deviation divided by x bar. Okay, now what's new this week? Well, here's a little, whoops, thought I'd highlight that. Here's our probability square. Okay, so we're about to go over some of these rules. And then last week we also had started z-scores down here, so that's under probability distributions. We'll talk more about that, but z-scores can be used for probabilities, and we're going to be doing a lot of that next week. But so for now, it's under this mysterious section called continuous random variables, and you got your z-score formula. Alrighty, so please be aware of that. And knowing all that, we're going to be looking at these elementary probability rules. Some with more depth than others, okay? So here they are, the 6 rules: complement, union, intersection, addition, conditional probability, which is pretty tricky. That's why it's the last one. Multiplication is also there. Oopsie daisy. So prepare yourself for diagrams. So the complement, not A, of an event A is the set of all sample space outcomes not in A. So I said a bunch of words there. Let's talk about it. This is this is pronounced not A. What's the giveaway? Do you see this little bar on top? So if it's an average, like X bar, then we know that this is the mean, right? But in probability, when we put a line or a bar on top of a letter, it means not A. Okay, so you have an event A, and then you have event not A. So does it make sense if you look at this diagram? Here's my event A, and everything that is not A is highlighted in blue, right? So here's A, everything that's not in this circle is not A. It makes so much sense. So how would you calculate the probability of not A? Well, remember, all probabilities must add up to 1. Very important. So if I want to know the probability of not A, as long as I know the probability of A, I can calculate that. For example, say there's a 30% chance of no rain today. Well, what's the probability of rain then? Well, that would mean that if I go 1 minus 30%, so written as a decimal like this, or 100%, minus 30%, I would find out that there's a 70% chance of rain. Well, that is a demonstration of this whole A, not A concept. There you go. I won't say anything more because I don't want to overcomplicate an easy topic. Now, this is where we start getting more complicated. Check out this diagram. Let's talk about it. So, what is union and intersection? Let's talk. So the union of A and B are elementary events that belong to either A or B or both. It's written like this. So that is sort of, basically when I write it, it's going to look more like a U. Okay, so but this means A or B. Okay, so this symbol basically means or. Let's see what it would look like. I feel like I'm missing. No, I'm not missing anything. Just double checking my notes here. Yes, well, there you have it. So this is A or B. A or B is down here. Okay, so the event A union B, or A or B, is a shaded region. So you got event A and you got event B. Maybe there's some overlap between them, but A or B would signify shading in both of those circles. So what's intersection? Well, intersection of A and B are also elementary events that belong to both A and B. See the difference? A and B versus either A or B or both. Intersection is written like this. So it looks like an upside down U, and you can essentially think of this as meaning the word and. So when I see this, I say A and B. Well, this would be A and B, right? It would only be the overlap between those two events. So you might write probability of A and B, okay, meaning that it's that overlap, like that. How do you remember these two symbols? I had a lot of trouble, and it seems like a small issue, but it's very big in probability because you're going to see these symbols a lot. So here's how I remembered it. I one day was studying and I was like, okay, yeah, this is intersection, which is A and B. And when I was looking at this, I'm like, you know what? This upside down U is like one stroke away from being an A for and. Okay, that's how I remembered it. So I was like, okay, the upside down U, the one that I can turn into an A means and the one that is a regular U means or. That's how I remembered it. It seems silly, but it works. Wonderful, wonderful, wonderful. Okay, got to get all these definition things out of the way. All right, now the addition rule. This is on your formula sheet. The addition rule is right here. I am very nice and I write it with the or instead of using the symbol, trying to keep things as simple as possible in probability. Notice that this is that first formula we went over, that the probability of an event happening is the number of favorable outcomes divided by the number of possible outcomes, right? And now we've moved on to the addition rule here. So here it is again. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Why would we want to do that? So this is A and B. Well, we want to get rid of that overlap, right? Otherwise, if you add the probability of A and the probability of B, you're going to be counting some space twice. Let's go back to this slide. So you see here, look, this is the probability of A. It's all of this, right? So if I also add the probability of B, well, then I'm adding this section twice, right? I'm adding that overlap twice. That's why our formula subtracts it out so that it only gets counted the one time. Perfect. Very, very important, okay? It will also be maybe a little bit easier when we start doing some questions. So for now, I'm just going over all these formulas and it's sort of hard to put them in context. It is important to sort of preload this stuff so that when we get to the questions, it'll make a bit more sense, okay? Second point, A and B are mutually exclusive if they have no sample space outcomes in common. Okay, so mutually exclusive means, in other words, that the probability of A and B is equal to 0. So we're erasing that overlap. Okay, so when you have the two circles overlapping, this suggests that maybe they are not mutually exclusive. Okay, so when they're not mutually exclusive, that means there's some overlap. If they are mutually exclusive, it means there is no shared middle section. Okay, so if it's the case that the probability of A and B is 0, then the probability that A or B, remember that's called the union of A and B, will occur is this. Okay, so all we're saying is, look, this is our formula for probability of A or B. If this section is 0, well then the formula just becomes probability of A plus probability of B. When is this section 0? If the events are mutually exclusive. And we'll talk about that a bit more. Let's do some questions, because I've given you all these definitions and formulas and concepts. Let's do a quick question just to start seeing what it looks like in practice. So, mutually exclusive events. If you're randomly selecting a card from a standard deck of 52 playing cards, and we define the events like this, that J is the probability of randomly selecting a card that's a jack, and Q is randomly selecting a card that's a queen, and R is randomly selecting a card that is a red card. There's a few important things to know about a deck. If you're not familiar, I suggest you pause the video and just go Google like a standard 52 deck of cards. Unfortunately, in probability, we try to use concepts that most people know about. Most people seem to, at some point in their school career, most teachers will pull out a deck of cards and show you guys what it is. We will do other questions, but I will say it is important to know what a deck of cards is. So let me tell you what it is. There's 52 cards in total in a deck of cards. 26 of them are black, 26 are red. There's 4 suits. 2 suits are black, 2 suits are red, and each suit has 13 cards. The cards go like this, from ace, from A, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a mistake here, isn't there? No, 10, jack, king, queen. There is. It's perfect. It's perfect. Okay, so there's 13 cards in a suit. Every suit has these cards. They're either black or red, and the 4 different suits are 4 different symbols. I think it's like diamond, spade, club, and I'm drawing hearts. There we go. Perfect. Again, maybe I should Google it. I don't know. If you want to skip ahead, I suppose you could, but I'll quickly Google deck of cards. And let me see if I can find a nice image that sort of has all the cards. Yeah, that's not bad. I'm just on my other screen. I'll drag this over in a moment. Yes, this one looks nice. So here is a deck of cards. 52 cards. You got your suit, clubs, diamonds, hearts, spades. Clubs, there's 13 of them. They're black. Diamonds, red. Hearts, red. Spades, red. You don't need to know necessarily these, but you do need to know that 2 suits are red, 2 suits are black, and that there's 13 cards per suit. So, that being said, I'm going to minimize that. Back to work. Let's try this question. So, let us do it. Probabilities of cards. Use a relative frequency method to assign some probabilities. So, what is the probability of drawing a jack? Okay, so you got 52 cards, you're drawing a jack, so I'm going to go probability of jack. Well, remember, each suit has a jack, okay? Back to here. So every suit has a jack. So there's 1, 2, 3, 4 jacks in a standard 52 pack of cards. So there's a 4 out of 52 chance. Now you could reduce the fraction down. If you reduce it down, you get 1 out of 13. If you type it in on a calculator, I don't have one, but either answer would be fine. Sure, I can get a calculator. I have many calculators. I am a man of many calculators. So I got 1 out of 13, yes. So that is a 0.0769. There. So, which answer should you give? They're all good answers. Just got to give one of them. What's the probability of drawing a queen? So now we're starting like a new question, okay? So we have 52 cards again. Well, again, there's 4 queens, right? There's 4 of each card in every deck. So it's, again, 4 out of 52. What's the probability of drawing a red card? Now, probability of red. Well, remember, there are 26 red cards. So it's 26 out of how many cards? 52. This is the same thing as a half, or 50%, or 0.5. Now we're starting to use some of that lingo that I was showing you before. So remember, this is the symbol for or, right? So they're basically saying, what's the probability of getting a jack or a queen? Well, remember from our formula sheet that when you're finding the probability of an experiment, you tally up the number of favorable outcomes divided by the number of possible outcomes. So for this one here, well, there's 4 jacks. Oopsie daisy. There's 4 jacks. 4 jacks plus how many queens? There's 4 queens out of how many total possibilities? 52. So the probability of getting a jack or a queen is equal to 8 out of 52. Again, you can reduce it down, or you can simply just leave the answer like that. What about the probability of getting a queen or a red card? Well, this would be the same thing as probability of queen plus the probability of a red card. Now, is there any overlap? So are some queens also red cards? So we need to subtract probability of queen and red. Does this formula look familiar to you? It should, because it's the addition rule, right? Probability of your first event plus the probability of the second event minus any overlap they might have. So here's a practical example. We do have cards that are queens, so here's queens, that are also red, right? Out of the 4 queens, 2 are black, 2 are red. So we must subtract that overlap. I'm just going to continue down here. So what's the probability of getting a queen? Well, it's 4 out of 52. Plus, what's the probability of getting any red card? Well, there's 26 out of 52. Subtract how many queens are also red, right? Queen and red. Well, there's 2 out of the 52 cards are queen and red. So now you can go ahead. I'm just going to go over here because I'm going to run out of room. I prefer that you continue going straight down if you're doing an assignment or test. We have the same denominator. So adding or subtracting fractions, when you have the same denominator, we add the numerator. So 4 plus 26, subtract 2. That's going to give us 30 minus 2. It's going to be giving us 28 out of 52. And you can just leave your answer like that. And there you have it. Now, could we have done this question? Some of you who are super familiar with cards, could we have done this question without all the work of doing this formula? Yes. Yes, you certainly could have. You could have been like, well, queens or red. Well, you'd be like, well, there's 2 black queens, and then there's 26 red cards, right? And you would have gotten the same answer, 28. But that maybe is a very intimate knowledge of playing cards, okay? Last one. Probability of queen and red. Well, we sort of talked about this up here, right? But if I just asked you what's the probability of getting a queen and a red card, you would have to think and be like, well, okay, there are 4 queens, 2 are black, 2 are red. So there are 2 possible red queens out of the total 52 cards. There you go. I could go on forever and ever and ever with these types of questions. But I just wanted to show you 6 quick little examples that start to demonstrate the formulas in action and the concepts in action. Okay, we can do, like I will do some extra videos, and when we do our Zoom session together, I'll prepare some questions on, marbles and bags and things like that. Those are sort of the standard questions to help you understand probability. Okay, you won't mind me if I don't do a huge business focus just yet, because we're just trying to understand the concepts before dragging in, other complications, okay? So, next slide. Now we get into conditional probability, and then this is, I'm going to say, It's not fun, but it's also not super duper crazy once we get our minds wrapped around it. So, you guys can definitely do it. Let's talk. The probability of an event A, given that the event B has occurred, is called conditional probability of A given B, right? So you might think of it like, what does that mean? It's like, well, given that it's raining, what's the probability that I'm going to get wet today, right? So that would be a conditional probability. So one event has already occurred. How does that affect the probability of another event occurring? Okay, now the way that we write it is like so. So it's denoted like this. So it's kind of like a vertical line, and we would pronounce this probability of A given B. That's how you say probability of A given B. What does it mean? Well, here's the formula. The probability of A given B is the probability of A and B occurring divided by the probability of B. This is a stipulation. The probability of B cannot be 0. You can't divide by 0, right? You can't take four pieces of chocolate and divide it amongst your 0 friends. Like, it doesn't make sense. Like, how do you make 0 groups of something, right? So, the conditional probability that B will occur given that A will occur, well, all I've done here is I wrote it the other way, right? So, just showing you another way, like, probability of B given A would be probability of A and B divided by probability of A. Why am I doing this? Well, I just want to show you that because you're going to be using different letters in questions, right? So this is what your formula sheet says, right? We use A and B. Here it is, conditional probability. Now I did B given A here. But the important thing is do you know what goes in the denominator here and what goes in the numerator? So that was my whole point with this. Okay, so if it's A given B, in the numerator you always have probability of A and B. Okay, what goes in the bottom is whatever is here. So given B, you divide by probability of B. Given A, you divide by the probability of A. That's the important thing to remember. Okay, so very important. Let's try a question. Now, the easy version of this question, I give you a table, and the table is all filled out. The harder version of the question, I describe it to you in words. You can check the homework. I do believe there's a question like that in there. I do try to stick to the table so that there's a little bit less confusion. So here we go. Newspaper subscribers. Who the heck reads a newspaper? Refer to the following contingency table. Yes, these are called contingency tables. So they're just tables where we summarize basically probabilities or numbers that we use for probability. Okay, so little happy face. Now we know what a contingency table is. So refer to the following contingency table regarding subscribers to the newspapers for Winnipeg Free Press, which we're going to call W, and the Brandon Sun, which we're going to refer to as B. So what are the events? The events are that they receive the Winnipeg Free Press W, given that they receive the Brandon Sun. So there's 25,000 people who do that. And they do not receive the Brandon Sun. So notice that B and then not B notation. Okay, and then we got some totals along the side. Okay, so we got receiving the Winnipeg Free Press, given they receive the Brandon Sun, given that they don't, and then they do not receive the Winnipeg Free Press, but they get the Brandon Sun, or they do not get the Brandon Sun. So, for example, this one right here, they're not receiving the Brandon Sun, and they're not receiving the Winnipeg Free Press, so these are 10,000 people are not receiving any of those two newspapers. Okay, in total down here, we got our total number, 100,000 people are surveyed. Okay, by the way, I can start erasing numbers in this table, okay, and I'll be doing a question like that a little bit later, right? But if I gave you this number and this number, you'd be able to figure out that number, right? Because you know there's 65,000 people total in this row. If I gave you this, you would go 65,000 minus 25,000, you get the 40,000. Okay, I'm going to need to erase sort of some of my scribblings here, so probably not, but anyways. What is the bloody question, Demir? We'll get to it. Well, what are we asking for here? Well, I would like to know what's the probability of a randomly selected household receiving the Brandon Sun given that the household receives the Winnipeg Free Press. Okay, so I would not be giving you this, but you would be like, okay, got to be careful because this is one of those questions with conditional probability. So given they receive the Winnipeg Free Press, so there's the vertical line for given. So given that we receive this, we want to receive the Brandon Sun. So there it is. Probability that we receive the Brandon Sun given that we receive the Winnipeg Free Press. Well, the formula, I suppose this should be a W. Okay, the formula is that we look for the union of Winnipeg Free Press and Brandon Sun. So what's the probability that they get the Winnipeg Free Press and the Brandon Sun divided by the probability that they receive the Winnipeg Free Press? Well, the table makes this very easy. This first one, they receive the Brandon Sun and they receive the Winnipeg Free Press. So this is the probability of Winnipeg Free Press and Brandon Sun. It doesn't matter which order you write those letters in, right? It could be B and W or W and B. Okay, just point that out. So that goes in the numerator. What's the probability that they receive the Winnipeg Free Press? Well, that would be this column here. Oh, my bad. Look at your table very carefully. That would actually be this row, right? This row is receiving the Winnipeg Free Press. So in total, 65,000 people were receiving the Winnipeg Free Press, right? We got the two groups, the group that receives the Brandon Sun and the group that does not receive the Brandon Sun, but in total, 65,000 people get the Winnipeg Free Press. So there it is. Conditional probability is calculated by dividing these two numbers. Okay, I took a question that's relatively hard and I broke it down as easy as possible using the table. Okay, it can be harder if you don't have the table, if you need to construct the table. Obviously, that's the direction we're sort of moving to, but I just wanted to demonstrate this conditional probability concept. It is a little tricky to kind of wrap our minds around, especially when you just have all this stuff suddenly. Okay, I also said we talk about independence of events before we do some more questions. So, two events A and B are said to be independent if and only if the probability that A given B is equal to the probability of A. The condition that B has or will occur has no effect on the outcome of A. That is the definition of independence. Okay, two events are independent if the condition that B has or will occur has no effect on the outcome of A. Okay, lots of things are, seemingly independent. Okay, so I can't, of course, I can't think of a single one off the top of my head. I'm recording, I'm nervous, but yeah. As far as the formula goes, this is the formula that we use. Okay, equivalently, if I have the probability of B given A, it would be equal to probability of B to show independence of events. So what am I saying here? I'm saying, look, mathematically, if you want to show that two events are independent, you need to show that this probability is equal to this probability. Notice that whatever letter is here, whatever event is here, is the probability that's here. That's why I showed it to you in two different ways. Whatever letter is here is the probability that goes on this side. Okay, so in this example, the condition that A has or will occur has no effect on the outcome of B when it's written like that. Okay? Let's go and talk about our last example. So, remember the Winnipeg Free Press and the Brandon Sun example? So, our events of getting the Winnipeg Free Press and getting the Brandon Sun independent. Okay, so remember our example from before where we had the Winnipeg Free Press subscribers and Brandon Sun subscribers. I'm now asking the question, well, are the events of getting the Winnipeg Free Press and getting the Brandon Sun independent? If they are independent, then we need to show that, got to switch over here to my pen, we need to show that the probability of getting the Brandon Sun, given that you're getting the Winnipeg Free Press, is equal to the probability of getting the Brandon Sun. So yeah, we need to calculate this. Now, what is the probability of getting the Brandon Sun? Well, it's the probability of receiving Brandon Sun, right? So it's going to write B, divided by the total sample. right? That's that very, very basic rule of probability that we went over at the very beginning. So what is this? Go back to the table for a moment. What is the probability of receiving the Brandon Sun? So let's check out our columns here. Receiving the Brandon Sun. Okay, that'd be this column. So in total, there was 50,000 people out of the 100,000 receiving the Brandon Sun. Whoops, what a mess. Here we go. So 50,000 people getting the Brandon Sun out of the 10,000. Now, you could leave it like that. You could also reduce it because it's 0.5 or a half. You can use your calculator to do that. Okay, now we just calculated this in the last example, right? We calculated the probability of getting the Brandon Sun given that you were getting the Winnipeg Free Press, and we calculated that out to be 0.3846. You can go back and look if you don't believe me. So what's our conclusion? Is this probability equal to the probability of getting the Brandon Sun? The answer is no. So the conclusion is we needed to show that the probability of getting the Brandon Sun, given that you get the Winnipeg Free Press already, is equal to the probability of getting just the Brandon Sun. So this probability was 0.5. This probability was 0.3846. So they are not equal. So therefore, by the way, the three dots like that mean therefore, these are not independent events. There. Now, it is kind of an ugly question, not my favorite question, but I needed to show you because the course calendar says that we learn this stuff. So they are not independent events. We can say they are dependent. So the data seems to suggest that there is some sort of thing going on between the Brandon Sun and the Winnipeg Free Press. Whether you're getting one or the other might be dependent on whether you're getting one or the other. Fascinating. Perfect. The multiplication rule. These look really ugly on paper. When they come up in a question, I feel like it's a lot easier. You will feel as you're doing probability that it's very nebulous. Probability is an incredibly complicated area of mathematics. Okay, we are gonna barely scratch the surface of what probability is in this course. So if the problem is that no one question is going to necessarily be exactly like another one. Okay. Now we're going to stick to certain types of questions. So if you do your homework, you're going to start to notice like, there's like 3 or 4 different kinds of questions that we basically look at. Okay. But it is very complicated area of math. And you need to do as many questions as you can to basically expose yourself to just the wide variety of questions that come up. Okay. And we're gonna do a question that ties all of this stuff together at the end, okay? And then we'll do some more together. Okay, so the multiplication rule. The joint probability that A and B, which is the intersection of A and B, will occur is as such. Here it is. So probability of A and B occurring is equal to probability of A times the probability of B given A. Okay, so notice how these two things are the same. Or just this is basically another way, right? So what if it was probability of A and B and I was using probability of B? Well, notice that the B goes over here. Okay, so probability of B times probability of A given B. So if A and B are independent, then the probability that A and B will occur is simply probability of A times probability of B. So we can go A and B is just equal to probability of A times probability of B if the events are independent. And remember before I said I couldn't think of any examples. Well, what are some possible examples of independent events in real life? Well, our very first example of flipping a coin, right? So whether I get heads the first time does not affect my probability of getting heads the second time. Those are independent events. I can get heads 8 times in a row, and it doesn't change the fact that the probability of getting heads is 50%. The card example, those are dependent events, because if I'm interested in the probability of getting a jack the first time and a jack the second time, well, getting a jack the first time changes the probability of getting a jack the second time, right? Because there's only 4 jacks. So if I get 1 jack the first time, now there's only 3, and there's less cards as well, right? So those are events that are dependent. So you can't simply multiply the probabilities to get it. Well, let's continue. Let's get to the question. So tying it all together, we have a nice little question. Using the table below, which details a number of low-risk and moderate to high-risk companies that were surveyed in certain industries, answer the following questions. So what we got is, we got companies in aerospace, then food retailers, okay? And then we got low-risk aerospace, moderate to high-risk aerospace, and then some totals. I promised you that I would give you a question where the table is not completely filled out. It can be more complicated than this, but this is what we're going to begin with. So we don't have these totals over here, nor do we have the column totals or anything, and we're missing some info. So let's start by filling out the table. So if there's 6 low risk and 9 moderate to high risk, then in total we surveyed 15 aerospace companies. As far as food retailers go, well, we don't have this total. So we can't figure out this from here. But if you look at this column, I know that this is the column total, 19. So if there was 9 here and there was 19 total, there must have been 10 here. Okay? And then 15 plus 10 is 25 to give me my total N of 40 companies. So in total, I surveyed 40, which would indirectly let me figure out this, or I can just go 6 plus 15 and get 21. 21 plus 19 is 40. There's lots of ways to do it. So let's do some probabilities. Here we go. Find the probability that a randomly selected company is a food retailer. So I would write that as probability of food retailer is equal to, well, how many food retailers were there? There's 25 out of the 40. So this is about as easy as it gets. Now you can leave your answer like that, and I am going to. Find the probability that a randomly selected company is low risk. So we're just looking for probability of low risk. Well, how many companies in total were low risk? There's 21, right? So 21 favorable outcomes out of the total 40. Find the probability that a randomly selected company is medium or high risk. So probability that it's a medium or high risk company is equal to, well, what do we got? Well, we got a total of 19 out of the 40 companies. There you have it. It's just that easy. Part D, find the probability that a randomly selected food retailer is also low risk. Well, let's see. So probability that food retailer is low risk. Well, how many food retailers are there? There's 15 food retailers, and we have 40 companies. So there you have it. Again, you can leave your answer like that. Now, compare and contrast that with part E, because part E says probability that a company is a food retailer given that it is low risk. So watch out. This is very clearly a conditional probability question. Now, they can be worded a bit more sneakily, but for our example on this, I wanted to make it sort of obvious. So we are looking for a probability that a food retailer is chosen given that it's low risk. Okay? There's a couple ways to do this. You can use the formula, right? The formula would say it's the probability of food retailer and low risk divided by what goes in the bottom. What goes in the bottom is whatever is here, right? So probability of low risk. So food retailer and low risk would be 15 divided by, what's the probability that it's a low risk company? Well, that reduces the pool of companies to 21. So while it's a quick question, the concepts behind it are pretty tricky. Now, you don't necessarily need to use the formula. You can simply think about it and say, okay, given that it's low risk, that means that your denominator is 21. What's the probability it's a food retailer? You get 15. Okay, so if you have the table, it is a lot easier. You don't need to necessarily use the formula, but I do, recommend using the formula if you like. I can do it either way, but I've done a lot of questions, right? So contrast that with F. This question is just kind of one that's just thrown in there, but it's probability that a company is a food retailer or has a stock that's low risk. So if you're using the formula, we'd be going probability of food retailer or, so the U looking thing, or low risk. Well, that would be probability of food retailer plus probability of low risk. And then we got to subtract the overlap, right? So the overlap would be food retailer and low risk. This is just the formula from the formula sheet, right? It's the addition rule. It's A or B. So probability of A plus probability of B, subtract the overlap. Let's take a look at what that might look like in this question. So my food retailers right here are 15 plus 10, there's 25. So, whoops, I lost my ink. There we go. So there are 25 food retailers out of the 40 companies. Plus the low risk companies, well, 6 plus 15 is 21. So there's 21 out of the 40 low risk. Now, did you catch that? When we did low risk, we counted that 15 twice. That's why the formula has removed the overlap. So the overlap is the food retailers and low risk. So people who are food retailers and low risk, that is 15 out of the 40. So when you add it all up, 25 plus 21 minus 15, you're going to get 31 out of 40. And there you have it. Now, do you need to use the formula to do this question? And the answer is no, not necessarily if you're comfortable using the table. Now, I prefer to show you using the formula, but check it out. If I'm looking for food retailers or a stock that is low risk, I would just do it this way if I had the table. I'd be like, okay, well, there's a food retailer and there's a food retailer, and low risk companies. Well, here's a low risk company, and I've already included that. So 6 plus 15 plus 10, that gives me 25 plus 6, 31 out of 40. So you could have done it that way. Now, the question is, what kind of work do you show if that's how you did it? And the answer is, I suppose you would kind of show me, I don't know, you'd be kind of like, well, the food retailers, there's 25 out of the 40, and then low risk would be, 6 more or something like that out of the 40. So then you would say 31 out of 40. Basically, if you're not going to be using the formula and showing me all that work, you better make sure that your answer is super correct. Because if you give me just the answer with no work and it's wrong, like if you just said 32 out of 40, you get no marks, right? But if you show me all this work, and you just made a mistake in one part, you would get some marks still. Okay, so that kind of concludes our video. There's a little bit of a summary you can read through by yourself. Probability is deceptively simple. There's a lot of concepts in play in the back. The questions can all look very different and still have the same concepts. So it is very important, and I have it in red here, that you go check Moodle for the homework for week 2. Okay, I got homework and I got some solutions up there as well. Semi-detailed ones, and also I will post a few more example videos of just guided examples, and we'll meet on Zoom as well. So, thanks for joining me, and I'll see you next time. Bye-bye.